Hey guys, Math 5500. I think we'd all agree that the last video ended rather abruptly. So I want to give you some more information on the structure of the variance covariance matrix for our errors. Now, something that someone pointed out to me, I think it's a source of confusion, is this notation to me is just a little wacky where we look at this because S squared typically stands for the variance. And again, it's variance covariance matrix. I get that. But guys, I want to point out that this is just a covariance of our residuals. So I'm going to use this notation for the most of this video. So guys, it should follow that. I'm trying to figure out what I'm what I'm doing here. It should follow that the covariance of the error is just the covariance of the observed minus the predicted, and we should all be comfortable when we speak of this in terms of matrices. That this would just be y minus the hat matrix. So this is our response vector minus the product of the hat matrix and our response vector. And guys, this should follow that this remains to be the covariance of the identity matrix minus the hat matrix times the response vector. And as we saw at the end of the previous video, this turns out to be the mean square error times the identity minus the hat matrix. Now, in a class of this nature, this is important, and it's what we essentially are setting out to show. But I think that we should, or at least I should, go through kind of a proof of this. So, guys, something that we learn when we study matrices is that if B is some matrix that's derived by taking a vector y times a constant matrix A. Now, you may see where I'm headed with this when I say constant matrix A with the mean square error, and then y is just this matrix that could be thought of as I minus h because it's an n by n matrix. So something that we know is that the variance, the covariance of this B matrix can be rewritten, obviously, as the product of A and Y. But something that I don't think that is as obvious is that this can be rewritten as the A matrix times the covariance of Y times A transpose. So what we can do is we can come back up here and look at the covariance of the identity matrix minus the hat matrix times the vector y, response vector y. And what can we do? Using this, we can see that, again, covariance sigma square, I should have been consistent here, but I wasn't, so let's go here. So how can I rewrite this using this? Well, pretty obvious, right? The A is my I minus H, and then I get the covariance of Y, and this is horrible because I'm switching using the kind of conflicting notation within the same problem, but I'm doing it for a reason, times the I minus H transpose. Now, one thing we know here is we have I minus H, and the covariance of our Y can be rewritten as the covariance of our error matrix, or I'm sorry, the variance covariance of our errors, and I minus H transpose. Okay, now next thing we know is that this can be rewritten as I minus H, and this would be the mean square error of the identity matrix times I minus H, and we don't have transpose, and the reason is because of the symmetric nature of this I minus H matrix. The transpose is going to be equal to the, so I minus H transpose is going to be equal to I minus H. So we can think about this as bringing the scalar out if we want, sigma squared. So all we have there is the identity matrix, so it should be pretty clear that this can be rewritten as the mean square error times I minus H times I minus H. And probably one step, the I should be between here, and then because this is the identity matrix, it's just going to give us this. So I did actually skip a place there. And guys, this turns out to just be the mean square error times I minus H. And the reason it is I minus H turns out to have a property. It's idempotent, which idempotent matrix just says if A is idempotent, then A squared is equal to A. So there are certain matrices that we run into where when you multiply by itself, you get the matrix. So kind of cool. You can add that to your trash can of useless information. Actually, it's quite useful. So add it to your trash can of useful information. So guys, one more thing. Let's just think. What would that look like? The variance times the identity matrix. So guys. Being the mean square error times the identity matrix, and of course, guys, all that would look like would be on the identities, or on the diagonal, and then we'd have just zeros here. So that kind of fills in maybe the one spot that was maybe just a little clear in what I provided on the other page. Okay, on to bigger, better stuff. Now, what would this look like? What would this whole covariance of E, our errors, which is the mean square error times the I minus H matrix, what would that look like? Well, guys, what it looks like is this. The diagonals would give us the variance of E sub 1 and the variance of E sub 2. And guys, again, don't forget, this matrix here is an n by n. So, we have n observations, n observed data points. So this would be the variance of the error for the first data point, and so on and so forth. So we can go ahead, and this, of course, would be the variance of the error for the nth data point. Now, this other stuff that we get on the upper triangle and lower triangle, this would be just the covariance of E sub 1 and E sub 2 out to the covariance of E sub 1, E sub n. And, of course, down here we would have the covariance of E sub n, E sub 1. So if we're really concerned about the covariance between our errors, we really would just have to look at the upper triangle. Now, expanding on that just a little bit, this would therefore look like this being this matrix would look like the mean square error times 1 minus H11 and 1 minus H22, where these, it should be HNN, but I'm getting sloppy here, where this H11 is the diagonal element of our hat matrix, and H22 is the second diagonal matrix, and second element of the diagonal of the hat matrix, and so on and so forth. Okay, this element right here, what would that look like? So I guess it would be minus H12, because this is all 0, right? And minus H13, and of course minus H1n, and of course this would be minus Hn1, right? Yeah, all right, cool. So what we can say is each element, so these 1 minus Hij is the ijth element of the I minus H matrix. Okay, so the variance of the ith residual can be found as the mean square error times 1 minus the element on the diagonal of our hat matrix. And guys, since we know that variance has to be greater than, in general, variance has to be greater than or equal to 0, then it would follow that 1 minus HII has to be greater than or equal to 0, which implies to us that HII must be less than or equal to positive 1. So what happens here is that when HII is close to 1, it tells us that the variance of the ith residual is small. And it should follow pretty clearly, right? If we get a larger number here, subtracted from 1, well, then we get a smaller result. So again, HII close to 1 tells us that the residual is small, and therefore that observed point is close to our fitted line. So have a fitted line. That point's very close. So it would have a large HII value. That would have a smaller. Okay? So guys, at the end of the day, I really can't make this difficult, and I wouldn't anyway. A small variance tells us what? That our observed value and our predicted value are very close. All right, guys, that's all the damage I can do here. I don't think there's anything else I really where I want to go with this. Yeah, I think we're good. So take care.